Hello, my name is Vasileios Sougkakis, and today I will present you a set of tools and the integrated process that has been developed within the framework of the RINNO project to support the renovation of buildings at the design stage. First, let's start with some background on the status of the energy renovation of EU buildings, which has led to the RINNO project. Currently, the EU there is great saving potential from the deep energy renovation of buildings, since it is estimated that 75% of buildings have poor energy performance, while also it is expected that between 85 and 95% of the buildings which are being used today will still be used by 2050. At the same time, current renovation rates are very low, approximately 1% for common renovation and 0.2% for the deep energy renovations. And several key barriers have been identified for this low uptake of renovation rates, which have been grouped in technical, financial, social and regulatory barriers. A few words about the RINNO project. It's an EU-funded Horizon 2020 project which aims at increasing the renovation rate of EU buildings by delivering a set of innovative processes and products for all stages of a renovation project. These phases are the planning and design phase, the construction phase, and the use phase of the building after the renovation. And these processes and products are supported by a cloud-based platform, as well as novel funding mechanisms. In the work that we present here, we focus on the planning and design phase, and the RINNO approach on tackling on many of these identified barriers for the design phase. So, what does RINNO consider? It considers a holistic approach for the design stage of buildings, where potential renovation scenarios are simulated and assessed against various performance aspects. So renovation scenarios are assessed in terms of their energy performance, environmental impact and life cycle costing, financial investment performance, as well as user disruption and construction waste. After this analysis, the optimum scenario is selected based on the user preferences using a decision support system. And finally, for the selected scenario, the optimum work sequence is generated based again on the user's preferences through a suitable software. So, in order to do this analysis, several software tools have been developed, starting off with the simulation tools, which conduct the energy, the life cycle assessment, and the user disruption analysis. These are three tools and are all grouped in what we call the RINNO simulation and assessment toolbox. And the results of this analysis are expressed in suitable KPIs and then are fed to them RINNO Optimizer and Planner, which is another component of the RINNO platform and has two software, the renovation scenario DSS, which based on these KPIs selects the optimum scenario, and then the job scheduling optimizer, which generates the optimized work sequence for that selected scenario. In the next slides, we will go through the brief description of these tools. Now, starting with the energy analysis, this is conducted with the Intema building tool. Intema building is a specialized software for building energy simulation and was developed using the Modelica language in the Dimola environment. The tool has been validated against the relevant ISO standard, as well as similar well-established commercial software, and it is able to model multiple energy production and storage systems in buildings. The tool is user-friendly and allows non-energy experts to conduct energy analysis. The analysis is conducted through the graphical user interface, where the user enters the required inputs, such as building geometry, material properties, etc. And the appropriate structure of the Modelica model and the relevant libraries are then automatically generated at the back end. Also, the tool is able to retrieve input data from external sources, such as weather data repositories. When the analysis is finally finished, the heating and cooling loads of the building are determined, and also the energy-related KPIs that are used in the selection of the scenario are calculated. Furthermore, energy time series data are produced, and these are used in the life cycle cost analysis, as we will see in the next slide. The life cycle assessment and the life cycle cost analysis is conducted with Verify platform. Verify is a web-based platform which conducts the LC and LCC analysis of buildings, following the methodologies of the relevant standards. The analysis is conducted by setting up an electrical, a thermal and investment plan, where the user defines all the electrical systems, the passive and active systems of the building, as well as economic data required for the analysis. In order to calculate the relevant environmental and cost KPIs, the tool is using its own private database, while it can also connect to external databases and tools. For example, the simulation energy data regarding the use phase of the building for the planned renovation scenario are retrieved by the Intema building tool. Finally, the tool may also connect to monitoring sensors, which are installed in the buildings, and calculate environmental and cost KPIs in near real time. Next, the analysis of the levels of user disruption and the expected waste produced during the renovation is conducted with the techno-economic assessment tool. The tool follows a BIM-based approach where the user imports the BIM files and defines the scenario to be assessed. A renovation ontology has been developed, and this maps specific renovation actions to the investigated renovation scenarios. The building elements and the material quantities are then generated by the BIM model, and these are associated with the renovation activities. The tool then conducts the analysis and estimates the disruption levels and the expected amounts of generated waste, as well as an initial preliminary estimation of the duration of the renovation. With regards to disruption, 4 types of disruption are considered. This is disruption in utilities, in traffic, physical space, which is when the occupants need to leave the building, as well as disruption in internal environment, which is noise, dust, odor, daylight, and daylight reduction. When the analysis is finished, a set of indicators are produced, which are then fed to the RINNO optimizer and planner. The tools presented earlier conduct a multi-criteria assessment of the scenarios and produce a set of KPIs. These KPIs are then used by the renovation scenario DSS tool to select the optimum scenario according to the user preferences. The KPIs that were generated are stored in a database, and the analysis is conducted by a multi-criteria decision-making method. In order to select the optimum scenario, 2 types of input are required. First, the results of the analysis. This is the KPIs that have been stored in the database, and these are retrieved by the DSS. The KPIs are grouped in 4 categories: energy, environmental, cost and financial, and user disruption. Next, the other type of input which is required is the user input. This is the user preferences, which are entered through the graphical user interface. The user selects the scenarios to be compared and also may choose specific indicators to be used in the selection process. The user may also apply specific weights of importance to each category. With this type of information, the tool then derives the best renovation scenario according to the user's input. Finally, the job scheduling optimizer produces the optimum work plan for the renovation scenario that was selected earlier by the renovation scenario DSS. The optimum work plan is considered the one that minimizes the duration of the project and or the disruption to the occupants, while also respecting a set of constraints that was set by the renovation manager. The JSO solves this resource-constrained project scheduling problem by applying one of the 4 following methods: integer linear programming, genetic algorithms, priority rules method, or a hybrid method that was developed for the purpose of RINNO. To do the analysis, specific input is required from the user and from other RINNO tools. And more specifically, the job scheduling optimizer receives input regarding job specifications from the techno-economic assessment tool, and such input relates to work duration, persons required, related disruption, and jobs precedence. And also receives input from the user through the graphical user interface, and the input required is the available budget for the renovation, the number of workers, etc. Most of the tools that were presented may be used individually to conduct specific type of analysis, but in order for a user to be able to conduct a holistic analysis proposed by RINNO for informed decision making, the assessment and communication of all tools is required in order for the whole process to work in an integrated manner. The tools are exchanging different types of data between them in order for every software to be able to have all the available inputs to conduct the analysis. Such data are text data, scenarios description, the energy time series between thema building and verify, the KPIs that is used for the selection of the scenario, and the job setup information for the optimum work plan. Most of the applications are web-based, so they are communicating through APIs and exchanging JSON files. In order for the T tool, which is desktop-based application, to communicate with the other tools, this is achieved through an SFTP server where JSON and Excel files are exchanged with the other tools, as shown in the graph here. In these next slides, we will go through an example of the real-life application of the RINNO approach in one of the demo buildings of the RINNO project, where the innovative processes and technologies are demonstrated. The Greek demo building, which is the example that we see here, is located in the Tavros area of Athens and is a 4-story building constructed in the 1950s. The building envelope is uninsulated and there is no central heating. And the 8 flats that are privately owned have individual heating systems, mostly air conditioning units, old inefficient air conditioning units, and few individual boilers. Within the RINNO project, the Hellenic Passive House Institute will upgrade the building to a positive energy building, which will achieve the Passive House Premium certification. Within the context of the RINNO project, several potential renovation scenarios were examined, and here we will see we'll see 2 of the scenarios presented, Scenario 1 and Scenario 3. Scenario 1 is a common renovation, which includes some basic measures, and Scenario 3 includes additional measures on top of the ones that are considered in Scenario 1. The results of the analysis of all the tools regarding the energy, environmental, cost and financial, as well as user disruption categories are presented in this slide. In total, 27 indicators are calculated by the simulation tools, and these are taken into account for the scenario selection process. We can see that based on the analysis of the DSS, Scenario 3 was selected as the optimum one for the renovation. It was found that Scenario 3 performed significantly better in the energy and cost categories, cost and financial categories, as well as marginally better in the environmental category, while Scenario 1 was only marginally better in the user disruption category. It should be noted here that Scenario 3 had a higher initial cost than Scenario 1, and it is common practice that renovation projects are often selected based on the capital cost. So if that was the case, Scenario 1 would have been selected instead of Scenario 3. In this case, we can see clearly that it's a clear demonstration where the RINNO approach led to the optimum renovation alternative, the selection of the optimum renovation scenario in the long term. Furthermore, the JSO generated the work plan considering 2 cases. One where there are 4 available workers for conducting the renovation, and the other where 10 workers conducted the renovation. And in the second case, several jobs were parallelized as there was more workforce available to conduct the works, and the renovation time was reduced to 132 days from originally 343 days. The tools that were presented in this work and the integrated process demonstrated through the case study deal with the design and planning stage of the building. However, RINNO includes additional tools and processes for the construction and installation phase of the renovation, so the output of this analysis is then fed to these tools to be used by the construction team on site for improving the construction process. Additional information on the other innovative solutions introduced by RINNO may be found in the project website by following the link below. Thank you for watching this presentation, and should you have any questions, please feel free to contact me in the following email. Thank you.